Welcome to the debate. Today we are looking at one of the most mesmerizing phenomena in gemology.
Oh, absolutely. They are just visually stunning.
Right. We are talking about the origins and classifications of natural blue, violet, and gray diamonds. And to do this, we are anchoring our discussion purely in the analytical framework established by Dr. Sally Magana, who has, mapped out exactly why these exceptionally rare stones look the way they do.
Yeah, her work is basically the standard for understanding that.
It really is. So the central question we are exploring today is a classic tension between nature and nurture. In understanding the complex coloration of these diamonds, should science prioritize the intrinsic elemental structure, meaning the atomic lattice and chemical impurities, or should we look at the dynamic phenomenological modifiers like environmental processes, radiation, and thermal history?
Right, the things that happen to the stone after it forms.
Exactly. I will argue that fundamental atomic substitution, specifically elemental impurities altering the carbon lattice, is the defining characteristic of these diamonds.
And I will argue that the true nature of their color is driven primarily by external processes and dynamic defect centers, such as irradiation and, thermal history.
Well, to kick us off, I actually want to frame this the way we might look at a masterpiece in a museum, say a classic Renaissance painting.
Okay, I like a good art metaphor.
Right. When we study a painting, we tend to attribute its fundamental identity to the painter's specific choice of pigments, the physical materials applied to the canvas from the very beginning. That chemistry dictates the art.
Sure, you're looking at the foundational ingredients, the raw materials.
Exactly. And when we are talking about diamonds, we are fundamentally talking about a highly organized canvas, a repeating structure of carbon atoms bonding perfectly to other carbon atoms. CCC. That is the baseline identity of the gem.
Agreed. You obviously don't have a diamond without carbon.
Right. So, in my view, the primary driver of color, and really the most logical basis for scientific classification, is intrinsic chemistry. Specifically, the elemental impurities that are introduced during the gem's very formation deep in the Earth's mantle.
But I would argue that relying entirely on structural typing is, it's far too static a way to view these complex gems. I come at it from a completely different way.
How so?
Well, to borrow your museum analogy, yes, the painter put pigment on a canvas. But think about how a painting is perceived centuries later. The aging of the varnish, the way the canvas has warped, the specific lighting in the gallery. The history of the painting becomes the art itself.
Okay, but it's still fundamentally the same painting.
Is it, though? It is not just what was painted, but what has happened to the painting since. The true drivers of the diverse blue, violet, and gray color spectrum are the external physical forces the diamond endures and the subsequent defect centers those forces leave behind.
Let's actually look at the data, though. Dr. Magana's framework identifies 4 primary causes of color in blue, violet, and gray diamonds. The first, and arguably the most famous, is boron.
Right, the classic blue diamond cause.
Yes, and let's actually talk about how boron works, because it is incredibly elegant. Boron cleanly substitutes into the carbon lattice. It replaces a carbon atom to create a CBC structure. It is basically an atomic swap.
Right, a neat little replacement.
Exactly. And this is vital because of how it interacts with light. White light hits that diamond, and the boron acts like a sponge for the red, yellow, and green parts of the visible spectrum.
It physically absorbs that energy.
Right. The only light that bounces back, the only light that makes it through that CBC structure to reach our eyes, is blue. This specific elemental substitution is so definitive that it single-handedly defines what we call type IB diamonds.
Yes, that is the definition of type IB.
Furthermore, hydrogen impurities act as the second foundational cause of color. In both cases, the elemental makeup is what matters. The chemistry is the gem's unalterable identity.
You don't think the boron substitution is enough to define the stone?
I think it is only a fraction of the story. You mentioned Dr. Magana's 4 causes of color, but you stopped at the first 2.
Well, they are the intrinsic ones.
But the third cause is irradiation. Looking solely at intrinsic elements like boron misses the broader, much more dynamic picture. It completely ignores how the environment actively reshapes the diamond's optical properties through intense radiation over geological time.
Reshapes, yes, but doesn't create from scratch.
I disagree. A diamond is often a record of environmental trauma, and that trauma is what gives it its unique color. I see why you think that, but let me give you a different perspective on how we should weigh those four causes against each other. When we look at boron and hydrogen, we are looking at strictly elemental impurities.
Right, elements.
They are intrinsic to the diamond's chemical makeup from the absolute moment of its crystallization. The elegance of the type IYB diamond is a pure chemical phenomenon. The architecture itself is built differently.
But architecture can be destroyed.
But it isn't a carbon lattice that has simply been damaged by the environment. It is a lattice that fundamentally incorporates a different element at its birth. That is why atomic substitution has to be the primary lens through which we view classification. Everything else is secondary.
But you are entirely dismissing the profound impact of that trauma I just mentioned. Let us look closely at the defect centers discussed in Dr. Magaña's analysis, specifically the GR1 center.
Okay, the GR1 center?
The nomenclature here is highly revealing. GR1 explicitly stands for General Radiation 1. This isn't a case of a neatly substituted impurity quietly sitting in the lattice like your boron example.
No, it's a structural defect.
Exactly. This is proof that an external physical event, specifically a bombardment by radiation in the Earth's crust, is just as capable of defining the diamond's color as its foundational chemistry.
But how is it doing that physically in a way that overrides the baseline chemistry?
By literally destroying the baseline chemistry. When a diamond is sitting next to radioactive minerals, alpha or beta particles slam into the diamond. It is a high-energy collision.
Right, radiation damage.
An empty hole where an atom used to be. And just like your boron atom absorbs red light, these physical holes, these vacancies, trap and absorb specific wavelengths of light.
Which alters the transmission of light, sure.
Drastically altering it. The blue or green colors we see in these heavily irradiated stones are the direct result of a dynamic physical event. It is not a static chemical recipe.
If radiation can entirely dictate the hue of the stone by punching holes in it, how can you claim that foundational chemistry is the undisputed king?
Because the foundational chemistry dictates what happens when that light is altered in the first place. Let's go back to our museum.
Okay, back to the art gallery. Think of the pure CCC carbon lattice of a type 2A diamond, a diamond with almost no nitrogen or boron, as a pristine, blank canvas. Elemental impurities like boron are the pigment.
Right.
Irradiation is merely changing the lighting in the gallery, or maybe, scuffing the varnish. The fundamental nature of the painting is still defined by its pigment and its canvas, not the lighting.
Scuffing the varnish?
Yes, the irradiation acts upon the existing structure, but it is the structure that holds the primary identity of the gem. Without the specific baseline lattice, the radiation wouldn't produce the specific optical effects we classify.
I'm sorry, but I just don't buy that. Let me tell you why. Your canvas and pigment analogy is incredibly neat, but it dramatically understates the transformative power of these external processes.
How so?
Actually, radiation isn't just changing the lighting in the gallery. It is taking a shotgun to the canvas.
A shotgun? That's a bit dramatic.
But it's true. It's knocking literal holes in the fabric. And the pattern of those holes is what creates the image you are staring at. And honestly, your static elemental theory breaks down completely when we start interrogating the complexities of nitrogen.
Nitrogen? I think nitrogen proves my point.
No, listen, it breaks down when we look at how the scientific community actually names and classifies these defect centers. You argue that the simple presence of an element is a defining factor. I argue that the process, what happens to the stone over millions of years, matters infinitely more than the mere presence of the element.
That is an interesting point, though. I would frame it very differently. I actually think the categorization of diamonds containing nitrogen heavily supports the elemental structural argument.
Really?
Yes. Let's break down Dr. Magaña's structural typing when it comes to nitrogen because it is a brilliant way to see how gemologists map these stones. We have type AA diamonds and we have type IB diamonds.
Right, the two main branches of nitrogen-bearing diamonds.
Exactly. Let's visualize this for the listener. Imagine the carbon lattice as a giant, crowded dance floor. Type IB diamonds are defined by isolated nitrogen.
Meaning they are alone.
Yes, that means single nitrogen atoms are scattered throughout the carbon lattice, dancing entirely alone, CNC. They are completely separated from each other. But then we have type IA diamonds, which are defined by aggregated nitrogen.
Right, they clump together.
Over deep geological time, these nitrogen atoms have moved through the lattice and huddle up together in groups of 2 or 3 or 4, CCN structures.
And that movement requires immense heat over millions of years.
It does. But notice how the entire typing system, type A versus type I, is completely dependent on mapping exactly how this specific element, nitrogen, is situated within the carbon lattice.
I see what you're saying, but
We don't name the type after the heat, we name it after the state of the element. Furthermore, when we look at specific defect centers causing color, like the envy center, it is literally called the nitrogen vacancy center.
okay, yes, the envy center.
The N explicitly stands for nitrogen. The scientific language itself prioritizes the chemical element. It maps the carbon baseline against the chemical deviation. To me, this proves chemistry is king.
That is a compelling argument, but you are cherry-picking the envy center because it conveniently aligns with your elemental theory.
I wouldn't call it cherry picking, it's a major center.
But if we zoom out and break down the nomenclature of the other major defect centers outlined in the framework, your argument that chemistry is king unravels completely. Let's look at the N3 and N2 centers.
Okay.
These are massive drivers of optical properties in diamonds. Based on your strict elemental logic, what does the N stand for there?
Well, if we are following the same logic as the NV center, I would assume it stands for nitrogen as part of the defect classification.
Yes, you would assume that, but it doesn't. The N in N3 and N2 does not stand for nitrogen. It stands for natural.
Wait, natural?
Yes, natural. It explicitly refers to a natural geological process of aggregation over time, as opposed to something synthesized or treated in a lab.
Okay, but
And it gets even more undeniable when we look at the H centers. Dr. Magana's framework details the H3, H2, and H4 centers. Now, in your framework, an H should logically stand for hydrogen, right?
because earlier I cited hydrogen as the second primary cause of color.
Exactly. So what does the H stand for?
I see where you were going with this.
The H in H3, H2, and H4 does not stand for hydrogen. It stands for heated.
I recognize the naming convention, yes.
But do you recognize the profound implication of that naming convention? Science chose to categorize these major optical centers not by the elements present in the lattice, but by their dynamic history.
They are categorizing the defect center, not the whole stone.
But the distinction is whether they were formed by natural, slow geological processes over eons, now as the end centers, or whether they were fundamentally altered by extreme thermal history, the heated H centers.
Right, the process.
The dynamic history, the natural versus heated evolution of the stone, literally overrides the static elemental makeup in the scientific nomenclature. The process defines the center, not the element. Science prioritizes the verb, not the noun.
I am just not convinced by that line of reasoning because you cannot have the verb without the noun.
What do you mean?
I do not deny that thermal history, the extreme heat of the Earth's mantle, and natural aggregation over deep geological time play a role in the ultimate presentation of the diamond. Of course they do.
Right.
But let's take a step back. What exactly is it that is being naturally aggregated? What exactly is it that is being heated? It is the elemental impurities.
But the heat is what...
You cannot have an aggregated nitrogen center without the nitrogen being there first. The fundamental building block must exist before it can be heated or moved.
But the building block alone doesn't give you this specific color.
But it sets the parameters of possibility. The type IA and type IB classifications, which map the isolated versus aggregated elemental structures, are the prerequisite baseline.
A baseline, sure, but not the defining feature.
The H3 or N3 centers are secondary phenomena operating on top of a primary chemical reality. You are arguing that the heat is the most important factor, but if you apply that exact same heat to a pure type 2A diamond, one with no nitrogen, you do not get an H3 center.
Well, obviously.
You just get a hot piece of pure carbon. The chemistry guarantees the potential. The atomic typing is the inescapable first principle of the gem's identity.
And you are suggesting the noun is the only thing that matters when the verb is what actually paints the stone blue, violet, or gray.
I'm saying the noun is the prerequisite.
If you have the chemical baseline but lack the heating or lack the natural process or lack the irradiation, you do not have the specific color phenomenon we are studying. It would just be a latent possibility locked in the earth.
But it's still a type IA or IB diamond.
The history of the diamond is written in its defect centers, not just its baseline chemical purity. And honestly, if you still firmly believe that intrinsic chemistry is the undisputed baseline, how do you handle the final cause of color identified by Dr. Magana?
You are referring to micro-inclusions.
Exactly. We have debated atomic substitution with boron and nitrogen. We have debated physical and thermal forces with irradiation and heating. But the fourth primary cause of color completely defies your atomic lattice framework.
I wouldn't say it defies it.
Micro-inclusions perfectly illustrate the hard limits of relying on an elemental typing framework.
How so? Let's unpack what a micro-inclusion actually is for a moment, just so we're on the same page.
A micro-inclusion is exactly what it sounds like. As the diamond is forming deep in the earth, it sometimes accidentally swallows up tiny, microscopic bits of non-diamond material.
Like foreign debris.
Right. We are talking about microscopic clouds of graphite or sulfides or other foreign minerals. They get trapped inside the carbon lattice like a fly trapped in amber.
Sure, it's an inclusion.
And these clouds of trapped debris physically scatter the light, creating gray and violet hues. Now, my point is this. These are not neat CBC atomic substitutions. They are not isolated CNC chemical deviations cleanly mapped onto a grid.
No, they are macroscopic on the scale of the atomic lattice.
Precisely, they do not fit into the elegant elemental math of type 2A, 2B, I, or IB. They are a purely physical, environmental intrusion that dictates the optical properties of the stone.
But they exist within the diamond.
But if intrinsic chemistry is the defining characteristic, how does your framework account for a primary cause of color that is fundamentally non-chemical and non-atomic? It is literally just debris caught in the web.
I see why you think that is a silver bullet against my position, but I would argue you are conflating an exception with the rule.
An exception? It's one of the 4 primary causes of color.
I will absolutely concede that micro-inclusions operate differently than boron substitution. They are indeed physical structural anomalies rather than atomic substitutions. However, the overarching scientific framework of gemology still fundamentally relies on the type classifications as the baseline of understanding.
Even when the color is caused by a chunk of graphite?
Especially then. Think about it physically. When Dr. Magana or any gemologist approaches a diamond to understand its color, the first order of business is mapping the CCC baseline against its chemical deviations.
Because it's standard procedure, not because it's the most important part.
No. You establish if it is type 2A, type 2B, type AI, or type IB first. Why? Because you must understand the foundational atomic canvas before you can accurately analyze the macroscopic inclusions that sit within it.
I don't see why the canvas matters more than the inclusion scattering the light.
Because if that host diamond wasn't a pristine, highly organized, transparent carbon lattice, you wouldn't even be able to see the micro-inclusion. The light wouldn't penetrate it. The micro-inclusions are fascinating modifiers, yes, but they exist within a host, and that host is defined by its elemental chemistry.
But if the host's defining characteristic, its literal visual identity as a gray or violet diamond, is caused by the microinclusion, or the GR1 radiation, or the H3 heating, then defining the diamond primarily by its baseline CCC or CBC structure is just reductive.
Reductive, it's foundational.
It tells us what the stone is made of, absolutely. But it completely fails to tell us why the stone matters, why it looks the way it does, and what it has actually endured.
It tells us its fundamental nature. Without the boron in a type 2b, you do not get that specific conductive blue phenomenon. Boron absorbs the red light.
Yes, boron is one way.
Without the nitrogen, you do not get the N3 centers. The chemistry is the script. The environment is just the actors performing it.
And without the radiation punching literal holes in the lattice, or the extreme thermal heating forcing atoms to migrate across the dance floor, or the natural aggregation over billions of years, that script is entirely unread.
Unread? Maybe, but it still exists.
The potential is completely unrealized or entirely altered. To me, a diamond is a physical recording of the Earth's volatile history.
Well, we have certainly interrogated the deepest structures of natural, blue, violet, and gray diamonds today through Dr. Magana's framework.
We definitely have.
And despite your incredibly vivid descriptions of environmental trauma and shotguns to the canvas, I maintain that the primacy of the fundamental atomic lattice and elemental substitutions is undeniable.
Of course you do.
The sheer elegance of a Type 2b diamond, where boron perfectly replaces carbon to create a CBC structure, demonstrates that intrinsic chemistry provides the fundamental, unalterable identity of the stone. The building blocks come first.
And I still just can't buy that a static view of chemistry is sufficient. The critical importance of dynamic processes cannot be overstated.
They are important, sure.
When we look at how extreme heating creates H3, H2, and H4 centers, how natural evolutionary processes define N3 and N2 centers, how radiation drives the GR1 center by creating vacancies, and how physical microinclusions alter the stone, it is undeniably clear to me that the final phenomenon of color is shaped by an active, dynamic history, not just a passive elemental recipe.
I think where we absolutely find convergence is in our immense appreciation for Dr. Magana's analysis. Her work reveals that natural blue, violet, and gray diamonds are highly complex, multivariable systems.
Oh, undoubtedly. They are absolute marvels of both chemistry and geology. While we maintain our respectful disagreement on whether the internal chemistry or the external environmental history is the most defining characteristic, we both recognize the profound complexity at play here.
Yes.
You really can't study one without eventually bumping into the other.
I completely agree. Understanding these rare diamonds requires holding both the static chemistry and the dynamic history in tension. There is still so much more to explore in the intersection of gemological chemistry and physical history.
There truly is. The science is as multifaceted as the stones themselves.
Which brings us right back to our museum, standing in front of that masterpiece. We can study the painter's fundamental pigments under a microscope, tracing their chemical origins.
Or we can step back.
Right. Or we can step back and see how time, light, and history have transformed the canvas into something entirely new. Both tell the truth of the masterpiece. Thank you for joining us, and we leave you to ponder, when you look at a diamond, are you seeing its birth or are you seeing its journey?